Thank you, Bastian, for the introduction and giving me an opportunity to present my research. So I'm Heda Ali, and I'm a senior research associate at Newcastle University, based in the School of Engineering. And have been working with Haley Fowler since 2018 as a postdoc. And yeah, so we do different type of stuff. Mostly we have done this temperature scaling stuff, and then we have been studying climate change impacts and risk assessment for seeing how sub hourly or sub daily rainfall has been changing, looking for the trends and seeing the change in the storm design due to the warming. And then we have also done several studies looking for the changes in the monsoon activity in the global south. And for past 2 years, I have been based in this different project called Hurricane, which I'm going to talk later. And my responsibility is to study, the changes or in the precipitation characteristics during the lifetime of the cyclone. So when it starts as a tropical depression, and then it transforms into the tropical cyclone. And if it keeps moving and goes extratropical transition and become a post-tropical cyclone. So in the initial slides, I would, talk about basics. To understand um, what the tropical cyclone and the different phases of the cyclones are. And how the precipitation looks like in different phases, and what are the drivers for the cyclogenesis for the cyclone or tropical cyclone transition to occur. So initial slide would be basic, and then I would go into the research and talk about two papers which we have worked recently and study and present their results. Yeah, so we are really interested in understanding, whether, with the climate change, these hurricanes are getting worse, because in the past, few years, we have seen a very severe, hurricanes, and which have gone to this category 5. One of the hurricanes in the 2013, this hurricane, Haiyan, broke all the records, which made a landfall in the Philippines, led to an interesting debate or discussion that should we try to add one more category, category 6, which is going to be more intense and extreme hurricanes. So, and just to look at the background of what's happening in the Atlantic Ocean, that every year, we are seeing that one or three cyclones of tropical origins are making landfall in the Europe. So they are basically originating somewhere in the Gulf of Mexico or in the Caribbean. Towards the eastern side of the U.S. And they have started uh, moving upward and towards migrating towards the Europe side. Within just these from 1980 to 2022, we have seen like 14 cyclones of tropical origin that have made landfall in the Europe side. And these are some important events in the past. Very important cyclone events which were of tropical origin, and they may have made landfall in the UK or the US side. And it is important to know that the cyclone, which has strong impact in terms of wind speed, may not have any strong impact in terms of precipitation, or the vice versa. If there are some examples when the cyclone was not very severe in terms of wind speed, but it was very severe in terms of precipitation. So we need to account both precipitation and wind footprint when we are looking for the severity or studying the impact of the cyclones. So, for example, just to show, in the last couple of years, from 1980 to 2022, if we use these index to define the extremeness of cyclones in terms of wind speed, the list goes like this. But the same event, which was very severe in terms of wind speed, the number is 2 for the precipitation footprint. So, a cyclone, which is not very severe in terms of wind speed, could be very severe in terms of the precipitation footprint. And in the coming slides, I'm going to talk why it happens so. Yeah. So just to start with the basics, the tropical cyclone, we see that the tropical cyclone is associated with a warm core and originated over the waters when the sea surface temperature is greater than 26 or 26.5 degrees centigrade. And what drives cyclone is the energy. So as the waters or the oceans gets warmer, it takes latent heat from there, and it leads to the convection, which starts the which starts changing the structure of the cyclone, make it more aligned and make it more symmetric, and that leads to the formation of a tropical depression. And if there is a sufficient energy to drive that, the tropical depression converts to the tropical cyclone. And as if these favorable conditions sustain, a tropical depression can convert to a tropical storm or to tropical cyclones, or the different categories. And if the cyclone sustains, it might go extratropical transition, which means that the cyclone starts losing its tropical nature and starts converting into extratropical cyclone. So, and this happens when the cyclone moves to this baroclinic environment, which has stronger temperature gradients. So it starts losing its symmetric and becomes asymmetric extratropical cyclone. So this figure just show that if there's a tropical depression and if the cyclone, if the depression has these favorable conditions, it can change to a tropical storm. And if favorable condition exists, keep existing, it converts into a tropical cyclone, which could be from category 1 to category 5, and eventually it goes under tropical transition if the conditions permit. It might undergo extratropical transition and converts itself to a post-tropical cyclone. So we are interested in studying the characteristics of precipitation for the different phases of the cyclone. How these, precipitation characteristics change. How the structure of the cyclone itself change, and how the precipitation associated with the cyclone in these different phases during their lifetime changes with the phase. Yeah. And just to tell more about the precipitation associated with the tropical cyclones in the different phases, so we know that, when there's a deep and convergence, there's a rise in the moisture, and the upper level divergence and the lower level convergence leads to these deep uh, systems, and the winds keeps rising, which leads to the formation of the cyclones. Yeah. And here right now it's axisymmetric, and if you see the precipitation footprint, it comes out very symmetric and very compact. And once the cyclones go this extratropical transition, the changes in the structure itself, structure of the cyclone starts, you see that the core becomes cold and it becomes very shallow, and you see the distribution of precipitation. It's no longer symmetric, but the cyclone itself becomes a font like structure, and the precipitation is elongated along the convergent side of the conveyor belt of the fronts in the extratropical phase. And so we try to understand, how this, symmetric and warm core cyclone converts into asymmetric cold core cyclone, which behaves like fronts and starts moving into greater speed. So for this, we use, in our field, we use this cyclone phase space, where the y-axis is the symmetry and x-axis is defines the cold core or warm core. So in the beginning, when the cyclone is in tropical depression or tropical cyclone phase, it is warm and symmetric. But but as it moves and takes energy, it goes towards the higher latitudes, and interact with this baroclinic environment or the mid latitude systems, it starts losing its warm core, and it starts losing its symmetry and converts into asymmetric, and eventually, it also starts losing its symmetric nature and become asymmetric. Yeah. And also, one interesting thing is, if you visualize the precipitation, it's very compact and around this center of the cyclone during the tropical cyclone phase. But when it undergoes extratropical transition, the precipitation becomes asymmetric and elongated along the warm conveyor belt, and the precipitation centroid, keeps moving towards the northeast and lies very far from the center of the cyclone. Yeah. So, and in the past, we have been observing that these cyclones originate somewhere in the Caribbean or the Gulf of Mexico. They have started migrating towards the Europe. Um, so this is the example of the storm Hoken, which originated somewhere in the Caribbean and started moving towards the South America, but it changed its mind. And this recurvature led to the movement of this cyclone towards the Europe. The blue dot shows this tropical cyclone phase, and this red dot shows the extratropical cyclone phase. So the extratropical transition happens somewhere here, and you could see the very strong precipitation associated with the cyclone phase. So obviously, a cyclone which during its journey, it has lots of moisture, so there would be lots of precipitation during its course. And as soon as the cyclone starts moving, and it the energy which drives the cyclone becomes less, so it loses moisture. So at the time of the landfall, you don't see very higher rainfall values. But again, for the extratropical cyclones, you could see that the centroid of the precipitation is very far, so it could have an impact in terms of precipitation footprint before even reaching the land, the before reaching the lands. So, and there are evidences that the regions of the tropical transitions, and they have started moving towards the pole, and you see that there has been a northeast expansion in the movement of the cyclones. So this is one of the papers, very important paper, which shows I mean, the ingredients which derive, the formation of cyclones, which variables, increase or decrease the formation of cyclones, and how the movement of cyclone is going to change in the future. Yeah. So, and just to talk last, this is the last slide which talks about the science of basics. So here you see the different ingredients, which support or which resist the formation of the tropical cyclone, or we call tropical transition. So the first one is sea surface temperature. So when you have, oceans, warming up, and there's a sufficient high temperature which leads to this uh, evaporation and convection, and this warm sea surface temperature leads to the favorable conditions for the cyclogenesis. And as the sea surface temperature keeps increasing, the moisture content also increases, and the capacity of the atmosphere to withhold that excess moisture also increases, which is supported by the Claisius-Clapeyron relationship. The temperature scaling stuff which we do, that for 1 degree warming, we see that 7 to 14% rise in the moisture holding capacity of the atmosphere. And the third one is the vertical wind shear, which designs, or which controls the formation of the cyclone. If you see a very strong vertical wind shear, that would try to tilt it and stops the formation. Stops the cyclone to rise up, and which would stop the formation of the cyclones. So the higher vertical wind shear, low to moderate, would favor the tropical cyclone development, but a high shear would suppress the tropical cyclone development. And the other one is the atmospheric stability. So we know that with the height, the temperature decreases. So the rate which decides, with what height, temperature would fall. If it is very stable, So so low stability, low, if it's very high stable, so that would suppress the formation of the cyclones. But if it is very low stable, so that would favor the convection and eventually the formation of the cyclones. And other thing is that how these tropical cyclones interact with the mid-latitude systems, which would lead them to move towards the pole and leads to, I mean, more tropical transitions. Yeah. So, I mean, I've been based in this Hurricane project, which is a UK funded project, and we as a team are interested in studying, uh, I mean, the whole journey of the cyclone. I mean, what factors, I mean, what are the drivers which lead to the formation of the cyclones, and uh, and what is the variability and the reasons for the genesis. And we also talk about the development, I mean, which keeps cyclone moving or keep sustaining them. And we also talk about the recurvature and the intensification. And work package 3 is responsible for this, is understanding the extratropical transition phase and how these cyclones of tropical origin interact with the mid-latitude systems and may lead to these post-tropical cyclones formation. And what hazards or impact do these systems, I mean, when they have a landfall, would bring to the UK or the US side. And we try to attribute these to the climate change stuff. Yeah. Um, One of the drawbacks, I mean, as I showed here, is that if you are, figure has been created using the IBTrACS data. And one of the limitations of the IBTrACS data is that, I mean, the focus is more on the tropical phase part, which is blue in color, but I mean, they stop, I mean, capturing or observing the cyclone journey once it becomes extratropical cyclone, goes under extratropical transition. So in most of the cases, I mean, when we see the trajectory of the cyclone, I mean, it doesn't appear to make a landfall because, I mean, the IBTrACS data is designed that way. So one of the novelty, I mean, from the project, which Stella Borden and Leosefin and these guys led, was to extend the IBTrACS data. So they have developed this RepTrACS using these reanalysis products. So they have a couple of reanalysis products, ERA 5G, ERA Q, and ERA 3, ERA 20C, and using different tracking algorithm. I mean, they try to stitch, I mean, two or three cyclones, which were actually a part of one event, but I mean, they have been reported, I mean, separately, or they try to extend a cyclone. I mean, so for example, here, I mean, a cyclone was reported just from this point to this point, but I mean, using different tracking algorithm like track and tempest extreme, I mean, and reanalysis product, they were able to stretch it further. So I mean, if you could just if you use this track from the IBTrACS, I mean, it wouldn't have made a landfall in the Euro, but after extending that using these tracks and the reanalysis, they are able to see, I mean, these tracks making a landfall, and we could do this impact studies based on that. So so let me, I mean, focus more on these on the part which talks about the characteristics of this cyclone in the different phases of the tracks and the precipitation associated with these tracks. So for this study, I mean, we are using IBTrACS data from 2001 to 2020, and we are mapping, or what say we are stitching. So if you visualize a track, it's like a latitude, and every time step is a latitude and longitude and some variables associated with those latitude and longitudes or each time step. So we try to understand that for each time step, I mean, we have plotted this. It looks like a trajectory of a cyclone. And what we are trying to do is that, I mean, IBTrACS doesn't have a precipitation field. So we are trying to use precipitation from the emerged GPM and trying to stitch precipitation values to each time step. Now the problem is, how do we stitch that? How do we add this precipitation field or shield to the each time step of the cyclone. So one easy way which this paper does that is it uses radius of cyclone influence as a proxy of the storm size. So IBTrACS provides ROCI values, radius of closed isobars for each time step, and we use this radius as our radius of a circle. And for each time step, we take all the precipitation from the emerge GPM for each time step, and we can. Sorry. Sorry, I think yeah, someone unmuted. Yeah. So we are trying to stitch precipitation to each time step. Yeah, and we are also trying to understand the translational direction. So for example, for each time step, this is the trajectory of the cyclone, and the translational direction, which is the bearing, would be the angle from the north. And we are also interested in looking for this black centroid. How far is the centroid from the center of the cyclone? Yeah. So if you talk about all the cyclones happening between 1851 to 2020, there were 2210, 2210 in number. And out of them, IBTrACS provide at least one extratropical cyclone step for 41%. And out of these 2021, 2210 cyclones, 38% of the cyclones went extratropical transition and they converted themselves to the post-tropical cyclone. So this shows the rate, percentage proportion that 40%, around 40% of the cyclones go extratropical transition and they become post-tropical cyclones. So the cyclogenesis locations, it happens mainly towards the eastern side of the Atlantic Ocean, western side of the Atlantic Ocean, towards the eastern coast in the Gulf of Mexico and the Caribbean. And if you plot all these time steps of this available tracks, it shows that it is more concentrated towards the eastern US part. We are very interested in the finding the position of the extratropical transition, the regions where this extratropical transition takes place and cyclones converts from tropical phase to the post-tropical cyclone phase. Yeah. And so now, we're trying to, what we know from the science, we're trying to use this data and see, what types of characteristics which we are observing here. So when we talk about the translational speed, so that is speed with which a cyclone is moving. So uh, since the extratropical cyclone, which is blue in color, and red is the tropical cyclone phase, since extratropical cyclone phase act as a front, and they move at very fast speed, which is visible in this plot, that the extratropical cyclone phase is associated with a higher translational velocity as compared to this tropical cyclone phase. And one important thing is the size of the storms. So you see that since after the extratropical transition, the cyclone is behaving like a front. And it has interacted with the baroclinic environment. So this interaction with the baroclinic environment, it makes the cyclone bigger. So the cyclones are bigger. The center and the centroid of the precipitation is very far from the cyclone center. Yeah. And you're talking about the intensity of the precipitation fields. So R1HI shows the time period of the duration for which the rainfall has been accumulated, and this shows the percentile. So the mean rainfall for 1 hour mean rainfall is lesser for the post-tropical cyclone phase as compared to the tropical cyclone phase. But interestingly, for the 24-hour periods, it compensates or it becomes more even for this post-tropical cyclone phase. Yeah. And when we talk about the spatial extent, this is important to understand the impact that you see a higher spatial extent. For example, if we just focus on this panel J, so here you see that the number of grids or the area, corresponding to the post-tropical cyclone phase is greater as compared to the tropical cyclone phase. which shows that the signature or the footprint of the precipitation associated with this post-tropical cyclone phase is bigger. And sometimes what happens is that the cyclone, even before making a landfall, can have an impact on the land areas because the precipitation is widespread. And since the precipitation is widespread, I mean, we could already have rainfall over the land areas. And again, this figure also shows the distance of the centroid of precipitation shields and the cyclone center. So for example, for the tropical cyclone phase, which is red in color, you see that the rainfall is very compact and symmetric. And in the post-tropical cyclone phase, the rainfall is asymmetric. Because of this asymmetricity, the centroid of the precipitation would be relatively far from the center of the cyclone. So we would see, or we would expect, that the centroid of precipitation is far from the center of the cyclone in the post-tropical cyclone phase. Yeah. And the last thing about characteristics of the cyclone, of the rainfall associated with cyclone, is the symmetry. I mean, we have a literature, I mean, says that, I mean, it's going to be asymmetric for the post-tropical cyclone phase, and we see that. I mean, you see very symmetricity, I mean, for these two, I mean, for the 3R and for the higher percentile threshold. But for the daily one, you see that the rainfall is asymmetric. For the extratropical cyclone phase, it's dipped towards the left side of the track when the cyclone is moving, and for each time step you're having a circle, so you're seeing that the rainfall values are more towards the left side of the circle as compared to the right side of the circle. So in all the previous slides, I have shown you that the translational velocity of the post-tropical cyclone phase is higher as compared to the translational velocity in the cyclone phase, tropical cyclone phase. I have shown you that the intensity of the precipitation is greater for the tropical cyclone phase as compared to the post-tropical cyclone phase. I've also shown that the areal extent, or this distance of centroid from the center, is greater for the post-tropical cyclone phase. So tropical cyclones are very compact, very organized. The precipitation is symmetric and it's around the center of the cyclone. But when the cyclone undergoes extratropical transition, it becomes a post-tropical cyclone. The speed of the tracks of the speed of the cyclone increases. They become as a front, and the precipitation reorganizes. It becomes asymmetric. Because it is asymmetric, the areal extent is greater, and the centroid of the precipitation is far from the center of the cyclone. Now, I told you that we made an assumption of using radius of closed isobar as to define the storm size, to make those circles to stitch precipitation to the tracks. But when you compared that to the other methodology, which I'm going to discuss, I mean, we see that radius of closed isobars, I mean, was underestimating the size of the post-tropical cyclones. So it's not appropriate. So when we were using radius of closed isobars, we were actually underestimating the size of the post-tropical cyclones, and because of that, we were underestimating the precipitation values. So if for conducting an impact study, I mean, we were using lesser rainfall, and so that would be wrong. So what we are trying to do now is to improve the methodology to properly stage, properly add, or properly map precipitation to these tracks. So we are again using the same precipitation product, but we are, instead of choosing those fixed circles during the lifetime, during the journey of the track, we are using this dynamically derived wind speed based radius, which I'm going to talk about in the next slide. So I mean, we know that, I mean, for the wind speed U10 and V10, we can split this wind speed into azimuthal wind speed component and the radial wind component. So if you see that, I mean, so it's the center of the cyclone, and it's it having vorticity and moving like that way. So the radial wind would be these red lines, and the azimuthal wind speed would be these green lines, tangential to the direction of the movement. Yeah. So I mean, you can visualize it's an hypothetical example. So what we are trying to do that this is the track. So each point denotes the time step of a track of a cyclone, and we are interested in mapping or stitching rainfall values to each time step or to each point. So for example, we take this red point as an example to show how this rainfall is mapped to this track. And for this red point, what we are trying to do is that we plot the distribution of the azimuthal wind speed. So it is the distance from the center. And so we know that the distribution of the wind speed would be different as we start moving from the center. So it would be the highest here. And as you go away from the center of the cyclone, the wind speed would start deteriorating. And yeah, so we are fixing a threshold that we're defining the size of the storm when the wind azimuthal wind speed dropped by 6 meter per second. So this threshold, this which comes on x-axis, is defined as the size of the storm for that time step. Yeah. So once we know the radius, I mean from here we would just draw a radius of that circle, and we will identify only the heavy precipitation parts. We are not interested in total precipitation because this methodology, I mean, is really good for the tropical cyclone phase when the precipitation footprint is symmetrical. But in the case of post-tropical cyclone phase, the precipitation footprint would be asymmetric. So for that, I mean, we are interested in taking only the heavy precipitation so that we could overcome the limitation of the asymmetry. So we are taking only the extreme precipitation part, and we are also calculating the centroid of the precipitation and interested in the distance of the centroid from the center of the cyclone. And we want to see that how these rainfall characteristics or the heavy precipitation is changing with the warming. So I don't know if people know about the temperature scaling stuff. So it's the way of estimating the temperature scaling. So we stitch rainfall with the temperature. We make pairs for each time step. We are not worried about the chronology. We just take the pairs of the rain and temperature, and these looks like that. And we just, I mean, divide all these temperature pairs, rain and temperature pair, in different bins, and we take some percentile like 95 or 99 percentile for each bin. And then we are only interested in those percentiles, and we fix a curve, and we take the linear regression and see that how it is deviated from this Clausius-Clapeyron relationship, which is 7% per Kelvin or per degree rising T temperature. Yeah. So here we are interested, I mean, to see that how heavy precipitation is changing with warming. So we have utilized different types of scaling variables or thermodynamic variables, which would be surface air temperature, dew point temperature, and sea surface temperatures, and surface equivalent potential temperatures. So each thermodynamic variable has their own uh, uh, limitations, or but I mean, we have used these comprehensive temperature scaling variables to do that. So we are also interested in seeing that how the storm size is changing with warming, and how these precipitation, heavy precipitation associated with this cyclone in different phases is changing with warming. So the first, this, I mean, this slide shows the distribution, or how the structure of this cyclone is changing with warming. So if you just focus on any one panel, for example, let's talk about this one, B. So you see the temperatures from 284 to 98. So with increase in warming, you see the decline in the size of the storm, or we say R6, which has been derived using this algebraically wind averaged, as I showed in the last slides. So for the tropical cyclone phase, which is solid lines, and this post-tropical cyclone phase is dashed lines. So you see a rapid decline in the size of the storm for the tropical cyclone phase with the warming, and it's very strong decline. Yeah. For the post-tropical cyclone phase, the relationship is poor because they 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 are not driven by the thermodynamics. They are more governed by these baroclinic environments. So the dependence on the thermodynamics would be less, and they are more dynamically driven. And you see that there is a sudden rise or little increase in the size of the storm with warming. So we are trying to see why. We see this rising limb. So to see that, we found that these higher R6 values with higher temperature are associated with those regions in the low Caribbean, where we see that the cyclones are bigger in size and they are moving with very low translational speed, which is again interesting. That imagine a cyclone with a stronger size, with a bigger size, which have more precipitation associated with it, and that is moving with a relatively lesser speed. So lower moving cyclones with more precipitation associated with them, so they would have a higher impact as compared to a faster moving cyclone over the regions. Yeah. So we are also seeing the dependence of precipitation centroid distance, which I showed in the figure. Yeah. So just to summarize this figure, it shows that with warming, the storms or the cyclones would become organized, and their precipitation would be closer to the center of the cyclones. And this is interesting and very alarming that we seeing a very strong relationship between the heavy precipitation or the mean intensity of the rainfall, which is exceeding 95th percentile. And this relationship goes up to like 21% rise per Kelvin rise in temperature. So you see like 21% increase in rainfall for 1 Kelvin rise in temperature in the for the rainfall which is associated with the cyclones. Uh, and in the literature, we have or the past studies, we have seen that this higher scaling comes because of the convective nature, and for the storms which have these stratiform rainfall, especially for the extratropical cyclone phase, the scaling is lesser. But again, it is alarming that we are seeing very high scaling rate for the tropical cyclone phases. And this is just not about the mean intensity, but it's also about the total precipitation associated with the cyclones. You see a very high scaling rate, up to like 32% per Kelvin rise in dew point temperature. And we're also seeing that the area uh, of the heavy rainfall, is increasing with warming. Yeah. So just to summarize that, and again here we are seeing that the translational speed is decreasing with warming. So you see, just imagine that a storm in the future, because of the warming, it becomes very slow and has high area of precipitation and bigger storm size. What an adverse impact it would make on the when it's moving over the land, over the oceans. Yeah. So the last component is to see that how can we uh, reflect, these increases in rainfall to the flooding over the UK. So this is one of the framework which I'm working right now, is to see first to identify very extreme events and drive for those extreme rainfall events, drive these model, which is one of the model is hydrology model is Shatron, and see and compare whether these reanalysis perform well against the observational head UK. And if Era 5, is able to perform good against the head UK. So the same models, the unseen data, it's a little bit technical for those who don't know about the unseen data, but just to give just an introduction, that these unseen data are like, these are the hindcast data, and we are interested in studying some plausible scenarios. They never happened in reality, but there are chances that they might happen. So what would be what would happen in those situations or those scenarios? So since era 5 and this unseen data has same IFS model or the base model, I mean, if we are able to show that era 5 performs well against the observation, we could use, I mean, this information to use unseen data to study the impacts uh, in terms of flooding. So I have been running this Shetron model and using era 5 and head UK, and found that one of the catchments, which is near Bath, its name is Avon. And the had UK, I mean, this performs really good against the observational CH care, but the Era 5 performs really bad, I mean, for this catchment. And for many other catchments, we see very high biases in the rainfall in Era 5 against the observational head UK. And even for a lesser bias, we see a greater biases in the discharge, which is being driven by the Shetron. And the timing, even the era 5 is really bad in capturing the timing of the peak flow events. Yeah, yeah. And this is just a case study of identifying some worst examples in the past few years based on RSSI index, which takes wind and precipitation both. And I'm interested in running Shetron model for those events and see whether we see a widespread signature of flooding across the UK because of these events or not. Yeah. So I would just stop here, I think, uh, and see if you have any questions or confusions, or if you have any suggestions. I mean,